All right, welcome to Lab 8. This is called the impulse momentum theorem. It goes hand in hand with the law of conservation of energy. This is a vector law, whereas energy was a scalar. It's much more enjoyable when you can use scalars, but the consequences of the law of conservation of momentum are really astounding. And we'll have a bunch of demonstrations in class. But up here right now I can demonstrate a couple of the consequences of the law of conservation of momentum. And remember, this is called the impulse momentum theorem. All right? So anyway, this guy here plays for the Giants. He hits the ball, and he doesn't hit it anywhere near the sweet spot. And so when he does that, he creates a huge bend in the bat, which cracks the bat. The cool thing is that he hits the ball a second and even a third time. I can't really tell, but if you, I guess, really slow down the frames, you can see the ball gets hit twice at the end of the bat. I'll just take their word for it. But I read up on it. It was during one of the World Series games. And I think he pulled a base hit off of it, which was a critical run, a critical hit. But anyway, what's happening is you see the ball's coming in, and the bat puts a big whopping force on it. So force of bat on ball. Well, you know, from Newton's third law, for every force, there's an equal and opposite force. By the way, it's a normal force of the bat acting on the ball, and the normal force of the ball acting on the bat. So the ball gets stopped moving this way and forced to move that way. Well, as far as momentum goes, and momentum is, let me write it on the board so you can see, momentum, P, they use the symbol P, is equal to the object's mass times its velocity vector. Okay, so velocity vector, the ball's coming in, so if you call that direction positive, then when it comes out, it's heading in the negative direction. So the ball undergoes an impulse when that force is acting on the ball. Well, likewise, you can see the bat. The bat got the same exact force applied to it. So you see the guy swinging the bat, and you can see that the bat's swing has been slowed down dramatically because the ball is pushing on it in the opposite direction. So it causes the bat to slow down. In fact, it caused the bat to slow down so much that the bat bends and breaks. All right, here's a couple more cool pictures. Here is a Titleist golf club hitting a golf ball. And you can see as it delivers that normal force, which is called impulse, the time over which the force is delivered is called an impulse. And it causes the ball to take off from the tee. So it was not moving to begin with, momentum 0, and now it has a tremendous momentum this way. Now what happened to the club? Well, if you ever swung a golf club and didn't hit a ball, then you see the swing of the club, the speed down there at the bottom, just continues with its normal value. But if you contact the ball and you're putting all that energy into the ball, then it's feeling a counter force, a force opposite from the ball on the club, and slows it down. All right, and that whole period of time, that's called an impulse. And then one more, my son and I, son Tom, who's taking a video, he was looking at the ball. He goes, man, that thing's not even rotating. So it looks like this super slow-mo, because the person who hit the ball probably hit it so hard that there was very little rolling. So it slid across the felt of the pool table, but you can see when it hits the wall of the pool table, the wall provides a force over time and turns that ball around. Now you know, the ball is also trying to move the pool table, but pool tables are really massive. So you don't really see the effect of the force of the ball on the pool table. All right, so that's basically what we're going to study in this lab. Very cool topic. And I didn't put my little slide changer into the computer, so I'm just going to run over there and do that right now. There's no need to stop or anything like that, because the nice thing is these Logitech dongles respond right away. Okay, so let's do the math on this. So Newton's second law, written in its original form. Now here's old Newton right here. There's his signature. And he was born on Christmas Day in 1642. He lived till he was 84 years old, which is amazing back then because the average lifespan back then was somewhere like in the late 30s. 36, 37, 38. But anyway, the Newton's second law says the momentum of an object acted upon by a net force changes in the direction of the force according to this equation right here. F net equals dp dt. Now what did we use up until this time? We use F net equals ma. Well, you see P has m in it up on the board there, m, and it has v. So if we pull the m out, then dv dt is acceleration. All right, but actually this equation right here also works for rockets taking off. And you know when a rocket takes off, it shoots exhaust gas out the back end. That exhaust gas has mass, and that creates an impulse. Okay, an impulse. All right, so now we're going to integrate this thing. So we're going to take dt, throw it over on the other side, and we're going to integrate dp. By the way, what's the integral of a differential? Well, it's just delta whatever the quantity is. So the right side of the equation is super easy. So delta minus p initial. And then on the other side is the integral of the force over the time when the force is applied to when it stops. Now notice, I didn't do that integral because you have to plug in what the force function is. How does the force change as a function of time? All right, so we're going to actually look at that numerically. We're going to do numerical integration rather than analytical integration, which would be what you would do if you had an equation for the force in terms of time. All right, now both of these things are called impulse, and the symbol is big letter I. Okay, so this is an impulse, which is exactly the same as seeing the change in momentum of an object. Well, if you're not interested very much in the force as it's applied over time, you see how easy it is. All you have to do is measure the speed, the velocity of the object before it gets hit by the force, and get the velocity times the mass after, and you got the impulse. All right, pretty cool. Anyway, let's look at the unit before we go on any further. So the unit for momentum is the kilogram times the meter per second. Notice it's not meters per second squared, that's acceleration. So this is the momentum unit right here, but we can also write it as Newton times a second. Okay, if you look back up here, you can see newtons times a second is the same as kilogram meter per second. Okay, so you can use either unit. For our lab, though, the really nice unit would be the Newton second, because there's nothing in the denominator. All right, let's go to the next page. Now, here's what a typical impulse looks like. All right, so you can see this car is coming in, smashing into the wall over here. And this would be a graph of the force applied to the car as a function of time. So if you integrate that thing, that value will give you this momentum, which is Pi, and then this momentum Pf. So Pf minus Pi, that's the area of that integral right there. So we're going to find the area under the integral, and we're going to compare it with a direct measurement of the momentum before and after the collision. They call that a collision, by the way. By the way, you walking across the room here, this is a collision. Okay, there's a force acting over time, which changes my momentum in the forward direction. All righty, I do believe that is it. Okay, so that's the end of the explanation, the background of all this. Then we're going to go on to the experiment. Really fun experiment. Okay, so hang right in there. We'll be right back. And, oh, did you stop yet? May the Lord be with you and keep you healthy and safe and peaceful. Okay, over and out.